Welcome to the Terminology Leading Practices stream at SNOMED CT 2025. Thank you to TermMed for sponsoring this stream. My name is Suzanne Santamaria and I'm a Senior Terminologist at SNOMED International. I'll be your moderator for today's session. We'll address all questions at the end of the presentation. For our online audience, please use the Q&A button to submit your questions to the presenter. For those attending in person, we'll use the microphones in the middle of the room here when the time comes. It's now my pleasure to introduce Dr. Stanley Huff from the University of Utah Department of Biomedical Informatics, who will be presenting Information Models and Terminology, two essential elements of semantic interoperability. Stan, over to you.
Thank you, Suzanne. It's a pleasure to be here today. I hope I can say something useful, and I'm excited you stayed around this long to be here. So thank you very much. It's an honor. And then just a warning, I have too many slides, so I'm going to go fast because I actually want, at the end, if people have questions and some discussion, so I'm going to try and get through it. But it's going to be stuff, if I was talking to a more general audience, I think I need to go slower, but I think it'll all be kind of familiar to you. So here we go. That's me. The two things I wanted to just give definitions for how I'm using the terms. These aren't necessarily global definitions, but for today's talk, I'm using the term concept models when we're talking about models that are used to guide and formulate codes when you're making codes in SNOMED or LOINC or a standard terminology. And I use information models when I'm talking about models that model the representation of data in the real world that you would use, for instance, as a guide for exchanging data between two systems or for a database or other things. So, two examples of concept models. One is like the 6-axis representation of LOINC or the SNOMED CT machine-readable concept model. And, those two actually line up pretty well because there was a lot of commonality and at least for the observable entity between LOINC and SNOMED. The fact that those things are so close together is from collaborations that started back probably in 2005 or maybe even earlier. So, but an information model then is a bunch of practical kind of information like, well, who's the patient? You have the code and value that's coming from a standard terminology, but then you could have other things like thresholds and cutoffs and interpretations and reference ranges and the method and whether it was screen or confirm reagents, etc. And so the information model shows the primary code, but then it shows all of the other related information that you need to try and understand the concept in its completeness. So then what I want to talk about is the important goal of information models, basically, is in support of semantic interoperability. And when I talk about, and what I'm trying to enable is not only exchange of data, but have a model that's standard enough and data representations that are standard enough that you can create an application and that application can be shared without people having to redo or remodel or do mapping of their local code. So the mental model is that the data that it's working on is standardized enough. It looks like when you're downloading something from Android or from the Apple App Store, you figure out, look at things that have 4 stars. You say, oh, I'd like to try that out, and you download it and you can start using it. Now, it's not quite that easy because there are all kinds of things that come into play. But the technical part of it should be that easy. But in medicine, then there's got to be training, there's got to be other kinds of things, and so you know that it's not going to happen that quick. Now, I'll go over this quickly, but I mean the way that the information models are used, and they're starting up here in the left-hand corner, you're creating information models that describe the structure and content of real-world data. And those models are used primarily 2 ways. One is that they come in and they're used then when you standardize data coming from all kinds of external systems to standardize it and put it into a common representation from which you can then do all of the other things that you want to do. And then the other thing that happens is that the information models are used in an open ecosystem where people can go in, they can use those models and develop applications, whether they're commercial or open for sharing, whatever. But they can come in, they can make their application here, have it certified, and then say, I'm certified to this standard. And that means that their application should be plug and play when you get it down here. And then, of course, what happens is down here, once you got the applications, then you do have some kind of marketplace or an app store of some kind. And people can download that or they can make their own apps. But then what you're doing then is, people are accessing and retrieving data and writing data actually back here. And that's, what creates a truly interoperable ecosystem. So they're very important in standardizing the data and then standardizing the way that you can access and use the data. And we'll say why that's so important. A couple of things here, this could be a personal health record rather than a, typical EHR, which is organization-based. And over here, this could be generative AI and all kinds of other agentic AI kind of stuff, et cetera. So I'm using, when I say application, I'm talking about software of any kind. So why do we need information models though? And it's because basically you have too many ways to say the same thing. So, you've got heart rate sitting, you've got heart rate supine, and those things are different, but you've got two different representations because you can have that more specific code that says this is a sitting heart rate, or you could use the more general code up here that just says I'm a heart rate, and then say, oh, and the body position was sitting. And so that's, part of the FHIR observation allows you to say that body position down here too. And then you've got the same thing with supine. But you have other attributes that you also put in here. For instance, you could put in here, was the patient exercising, was this pre-exercise, was it baseline? Was it during exercise? Was it post-exercise? What kind of device did I use? How did I know the heart rate? All of those kind of things. And so it basically, if you're not careful, you can end up with, for almost any data element, you can end up with 3 or 4 ways that can be represented. And you can't make software assuming that people do that all different. Even though they're using SNOMED codes and LOINC codes, they still are not plug and play interoperable if you don't say something more. So what we need to do then is we'd like to define a single preferred logical representation, because there are too many ways. But then you need to create maps because, in fact, whatever you choose as quote unquote the preferred way to represent the data, there are use cases that would say, oh, you need to represent it a different way. Typically, there are pre-coordinated codes are more often used in data entry because you don't have to click on as many boxes and put the data in. But the more post-coordinated representations are much better for analysis and analytics and clinical decision support and all of those kind of things. But this just comes from, real life. I've tried before. My starting preposition or assumption was you can use one model and everybody ought to use one model. And no, you can't. They just work around you if you in spite of everything else. And then I realized that there's actually good reason why it's not one model, but you have to be able to recognize synonymy and be able to represent it different ways, and then convert both ways from either pre-coordinated way to a post-coordinated way, or take the post-coordinated representation and know that there's a pre-coordinated code for that. So this is just an example of an actual information model for heart rate. there's the, very generic code for heart rate. You've got actually using SNOMED for the units of measure there. We've got, the patient identifier, we've got the method that was used, we've got the device, we've got the body location, body position, the exercise association, all of that sort of stuff. So the more global generalization that I would make is this one. So this is one slide that I think is maybe one of the most important in this presentation, and that is that you have the information model, and there are things in there like the patient ID, location testing, specimen source, the ordering clinician, the result status, the interpretation, et cetera. Those things are always in the information model. You never want to put, you don't want to put over in here Stan Huff's, serum sodium or something like that. And then depending on which kind of codes you're making, there are a set of things over here that are in the concept model and are always in the concept model. And so, these are the things that kind of distinguish and are always in laboratory data. But then there are things like the units of measure, the method, the device, the thresholds, the preconditions, the body location. Those things could be here or they could be here depending on your use case. And so what I would assert is that, from a modeling perspective, we have a choice, to represent things as part of that information model for the real world, or some of those attributes we could use when we make the codes, when we make pre-coordinated codes. So the challenge really is, how much meaning should be in the LOINC code versus how many more important facts are represented in other fields in the message. So we need these information models then to establish the meaning of data and information as used in medical reasoning and diagnosis, define the boundaries between the concept models and information models, and to establish a single preferred logical representation, but then be able to generate technology-specific profiles for data exchange standards, and then create maps between preferred representation and other allowed representations. So if I were to say this, the summary of this slide is basically, you've got a whole bunch of attributes, and those attributes are essential for the representation of the data in the real world. Some of those attributes, though, would be part of the concept model, and other attributes could be part of the information model. And you have to have the information model to really understand what the trade-offs are and the relationship between those different data elements when you represent the data. So this just shows the relationship and why it's important to have those concepts at all. And this essentially is the slide a little bit that says an answer to why AI doesn't do everything, won't do away with terminology and these kind of models. And it's because, the way we use this is that you start out down here with perceptions, which are just colors, things that you can see, sizes that you can measure, shapes of things, descriptions of mental phenomenon like pain or other kinds of things, heat that we can measure, et cetera. And then at that first level above that, you start saying, oh, this represents redness, this represents lymphadenopathy, this is, pain in the throat, it's a sore throat. The temperature is, here, so we detect heat, but now we've turned it into something that's actually measurable. We've got voltages and things that then tell us white counts, and we can look at colonies that are growing on an agar plate. And then from those things, you can make even further, you can make, through a logical process, you can say, oh, the fact that I've got these red throat and this cervical lymphadenopathy says I have inflammation. This says, oh, I've got a positive strep culture. That's high, so that's a fever. I can characterize it as a fever. I've got an increased white count. And then I can make, further logical decisions and say, oh, this represents acute streptococcal pharyngitis because of all of this data. And with further information that the patient had splenectomy or other things, you can say that the patient maybe is immunocompromised. So the point is, this kind of process is ultimately the thing that you have to use if you're going to validate the outcome of AI. This comes back to, we have definitions of what we mean by streptococcal pharyngitis, and to know that they really had it doesn't depend on the likelihood of the next word. It depends on actual logic from these things. And you need names for all of these things to do this accurately. And so, I like the quote here. Beginning of wisdom is the ability to call things by their right names. Go Confucius. Really like that. So, the thing that happens though is you have these general information models, and this is an example. So I say it's comprehensive, but example means that I might have left something out. So, but it gets across the point. So you say, okay, the information model has a patient ID, it has a LOINC code, it has a value, it has an interpretation reference range, and you can read the rest. And then there's the more mundane provenance information like collection date and time and specimen and lab time and who performed it and all of that sort of stuff. But one thing about this kind of information modeling is it's not an 80-20 rule. What you do is you put everything in here that somebody might use, but then what happens is we're going to specialize this so that the people who don't need that information aren't burdened by those attributes. So what happens then is we say, okay, if we're going to send Neisseria gonorrhea data, we don't have units of measure because this thing just says positive and negative up here. We don't have threshold or cutoff in this particular case. We've got interpretation, but that's optional. We've required is the LOINC code. Required is an actual value here, and then you've got a method. This one is required because we want to know what kind of DNA, but that's arbitrary. I'm just asserted that in this use case, but that in other use cases that could be optional as well. Reagents are optional. The specimen is required because even though from any if DNA is found in any specimen, the patient is infected. At the same time, it's very different to treat Neisseria gonorrhea meningitis versus Neisseria gonorrhea urethritis. So that's why that's required. But the point is, then when you're actually using this, only the things that are relevant from that more global model get represented in the actual use case that you're talking about. And so there's a lot of specialization that goes on, and you can see the specialization is not only loss of or taking out some of the attributes, but it's also fixing the value of the value sets that are appropriate in this case. So this is a value set of places that people actually do DNA, from which they create DNA specimens. And other things, the interpretations are going to be different for different kinds of activities, and positive, negative. Others could have positive, negative, indeterminate, etc. So it's specialized, and now you're dealing with what you really need in the real world, and you don't carry everything that's irrelevant, but everything you need is there. So you add anything anybody needs into the common model, and then you specialize that so that the people who are dealing in more general areas, the horses don't have to carry the weight of the zebras, if you will. So, and then there's just valuable inheritance that goes on, where you have a major class like observation. It has a set of attributes that are there. There's specialization that goes on to say, this is now a laboratory observation. And then there's specialization that goes on to say, there's quantitative lab, there's qualitative lab, there's titered lab, there's nominal kind of outputs, et cetera. And then you get specialization to say this is a hematocrit or a serum glucose or a urine sodium. And at the end, see, these guys, now the structure is fixed at this level, basically. And now all that's happening down here in the leaf nodes is that you're saying, well, what's the LOINC code that goes with that? What are the units of measure that go with that? And so these things have now a very common structure, and then creation of lots of these things goes really fast because all you have to know is, well, what is it? What are its units of measure? What is the value set, et cetera? So that's what's going on. So lots of different ways that you can represent the models. I'll just mention a couple that are very common. One is clinical element modeling. Abstracts, I guess almost all of these are very common. So archetype definition language, which is what OpenEHR uses. SNOMED expression language actually can represent the same thing. Unified modeling language, HL7 FHIR structure definition, extensible markup language, extensible markup language metadata interchange. So just to call out, there's a lot of work this has been done at SNOMED. There's a great web page for this and all kinds of fun things that have a post-coordination demonstrator and an implementation guide and a discussion of pre and post-coordinated expressions. And this is a description, but this is what the page looks like. And you have like bones, you have some pre-coordinated concept, and you say, oh yeah, and the bone for that is this, and the fracture is closed, and it's anterior displacement, et cetera. This is the actual SNOMED expression representation. So that's fun. So I'll go through this quick. Basically, this says you can automate the generation of these kind of information models using AI, mostly, but there's human review required. But using AI tremendously speeds up the process by which you can generate these kind of models. But then, just to show how it works in real life then, is you have that model library, and what you do is you have a transformation knowledge base and say, oh, from that model, I want to generate FHIR profiles. And so that's what's in this transformation database. It's basically saying, for the attributes and things that are in this library model, I know that the thing in this model that says code is actually the same thing as code within the HL7 FHIR observation, et cetera. And so that's what's in this transformation knowledge base. But I can do that same thing then and make an HL7 version 2 guide, or I can make a CCDA template, or I can make OMOP database column names, et cetera, and other things to deal with database. So these are all artifacts. But the thing is that you have a common worldview for representing the data, and then you can represent it in whatever formalism people want or whatever programming language people want. And that saves you a bunch of time because you don't have to make then transformations that go from FHIR to OMOP or from FHIR to version 2 or all of these guys, because they all derive from a common model. And then the creation of the actual mapping of things from a pre-coordinated concept to a post-coordinated, you can use SNOMED. So I can, if I have a code like suspected lung cancer, I can go to SNOMED and well, this is showing FHIR. What you want to do is make the model so that you get the pieces broken out. And the way you know how to do that, this is the slide I thought I was on. You can say, oh, I look up suspected lung cancer in SNOMED. It gives me the associated finding lung cancer unsuspected, and then it tells me, oh, and lung cancer actually breaks out into lung and cancer. And so you end up with that, and then what it represents then is, you can go directly basically from that pre-coordinated concept to the post-coordinated concepts. And then you can represent that. That's what you would represent in the map that shows you how to get from one to the other when you're actually translating data. Basically, it would say, if you extended this, it would say, if you had you know, if I get an incoming message where the disease says suspected lung cancer, I know that I can, in the post-coordinated representation, I know that that then represents a disease of this and a location of this and a location of that. Oh, that's a typo. That should say certainty there, sorry. And then you can put that into a database table. And so then when you're doing real data, what you're doing is you're bringing in real data, and then you have a transformation database like the one that we just described, and then you can automatically put this out. And the very best thing would be is that this thing is common, openly shared, so that people can transform without, you know, undue. And even better would be that they just call a service and say, I've got a fire thing with this in it, please transform it to the post-coordinated representation, or I've got a fire thing that's post-coordinated and I want to know the pre-coordinated representation. And that would be even better if we had a public service. You could just call and say, transform this data. So that's pretty much done. And I'm over.
We always have a couple minutes left. I don't know if you want to open for questions now.
Yeah, let's do questions now.
Thank you. Thank you so much, Stan. So we'll start the question period now. Just as a reminder, if you're in the room, please use the mic so everybody can hear clearly, and we have a number of people listening online too. Is there any questions for Stan?
Don't, you know, we need somebody to say, well, that's the stupidest thing I ever heard.
No, actually, I was going to say it was very interesting.
Oh, thanks.
It was a bit fast, though, but...
It was kind of fast. I apologize.
Yes. No, I had one slide that you showed that triggered me. It was the one with the many things on the bottom, and then the processes and the Confucius thing. Because for me, that's something that is very valuable to capture at the point of contact. The doctor who is seeing the patient, that's something I think should be in the EPD, in the patient file, that we have this structure and that we have that to be able to use it when we want to export our SNOMED CT codes in a meaningful way.
Yeah, no, and you know, that starts being on the border of this kind of information versus a knowledge base of how you use it. And so like problem knowledge couplers, you know, start representing that kind of logical information. Other kinds of things in diagnostic systems, you know, represent exactly that kind of knowledge. And it's a different kind of knowledge from textbook knowledge. And what I mean is the textbook says diabetes mellitus, you know, is a disease with relative insulin lack that results in hyperglycemia, blah, blah, blah. What we need in the real world is, no, hemoglobin A1C greater than this says he's diabetic. If the patient requires insulin to maintain normal glucose, he has insulin, she has insulin, et cetera. So, you know, you want that knowledge to be represented in computable knowledge. So those things that are those arcs in that slide represent rules that depend on real world observations to draw that conclusion. And that's a thing that we need to share too. We need to start thinking about sharing knowledge of that kind in a computable form rather than kind of the textbook representation of that kind of knowledge.
Agree more.
Thank you so much. So unfortunately, we're out of time. So that concludes this session. To our online delegates, you're welcome to remain here for the next presentation in the stream or navigate to a different session via the event lobby. Thank you, Stan, and for excellent presentation.